Hello, this video is to talk about bond enthalpy. It's using a past paper question from an OCR F322 paper from January 2011. So I'm jumping in partway through question 3 at part C. Standard enthalpy change of reaction can also be determined using average bond enthalpies. And here is one of the standard questions that comes up, the definition of enthalpy. Being a typical A-level student, you have decided that you will learn all of these the night before the exam. Being a typical chemistry teacher, I'm going to suggest this might not be the best idea, and it would be good if you could start learning them now. So, 2 marks available. You need to say how much of a thing and what exactly is going on. So I've put in brackets here to get us started. It's the enthalpy change when. Always want to start off with that. And essentially, the first part is for how much. 1 mole of bonds. That is going to get you the first mark. But you need to also specify where these bonds are and what's happening to them. So it's in gaseous, and then covalent I'm going to put in brackets because molecules kind of subsumes that, but in gaseous molecules. So that's always for gaseous molecules. And then the key bit are broken. So it's always an endothermic process. It's always about breaking the bonds. So 1 mole of them broken. You can see here in the table, positive, 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 always endothermic, always putting energy in to pull them apart. Okay. Explain the bonding in a carbon-carbon double bond using the orbital overlap model. So here I've drawn 2 carbons that have a single bond between them already and 2 other bonds. You know that carbon has to have 4 bonds. Well, to get a double bond, you have the single, you have 2 others, and then you need something else to happen. What you've got are the 2p orbitals. There are 2 of them here, and you end up getting a sort of, the key word you want in here is an overlap. Now you can, if you want, it's a sideways overlap, but these orbitals start overlapping, and what you get, everything else as before, you get a volume of space above and a volume of space below the original bond, and what you have to put in is that a pi bond forms. There are 2 marks. Know that a double bond, you want to mention about the pi bond forming. That's always going to be a mark. And here, when it's actually explaining how the orbital overlap, you need to show the 2p orbitals are what's overlapping. That's going to be the second mark. Right. So a bond is holding the 2 nuclei together. The sigma bond, which is the single one, is shown here, 345 kilojoules per mole. It says, why is the average bond enthalpy not twice the bond enthalpy of the single bond? Well, 2 times 345 would be 690. And you can see here it's only 611. Now before you panic, there's only 1 mark. You're not going to have to go racing off into a huge amount of detail. In fact, the numbers I'm doing here, you don't need to do for this. This is to try and help you understand it. If you had 2 single bonds, it would be 690. It's only 611. If we take 345, the strength of the single bond, away from the total for the double, you can see that the second part of the double bond has only got a strength of 266. Now, the 345 is the sigma, and this 266 is the pi bond. They're not actually in the optimum position for pulling the nuclei together. So we can simplify all of this down and simply put the pi bond is weaker than the sigma bond. Okay, or you could do the reverse argument and say that the sigma bond is stronger than the pi bond. If it was for more marks, you could talk about the fact that there's not as efficient overlap, but it's worth 1. If it asks you to demonstrate it numerically, you could do that. Hopefully all of this has explained it to you. Okay, on to the next part of the question, actually using these bond enthalpies to calculate an enthalpy change of reaction. So they tell you propane can be cracked to make ethene, and then it's also got a methane there. you have to use the average bond enthalpies in table 3.1, which is there. Now the first thing, learn these equations and make sure you can use them accurately. Enthalpy change is the sum of all the bonds broken minus the sum of the bonds formed. So look at your molecule and actually count what you're doing. You've got the CH's here, and I would go through and cross them off. There are 8 of them. And then the bit that if you don't check the molecule you might forget, I'm doing a different colour. Look at that, 21st century learning. There are 2 carbon-carbon single bonds. You need to make sure that you remember them. So that's 2 times 345, taking my numbers from over the page. I haven't learned all of these yet. So let's focus on the sum of the bonds broken. You have to break all of that, and the first mark here is forgetting that this is 3320 plus 690. So the first mark was forgetting 4010 kilojoules per mole. That's what you have to put in to rip all this apart. Now let's get the total of the bonds formed. Well, again, let's count them up. 1, 2, 3, 4, 5, 6, 7, 8. Oh look, there's 8 of those, which is 8 times 415 again, which is again 3,320. Okay, there's no other bonds here. There's one carbon-carbon double bond, which if we go back to our table over the page was 611. So 3,320 again for breaking and then making 8 of the CH bonds. So the total for that is 3,931. If you note, you're having to put more energy in than is given back out. So therefore this is going to be an endothermic process. So that's plus 79. Sorry, I should have written it there. Now, some of you who are really excelling at this will have looked at this and gone, hang on, I'm breaking 8 CH bonds and I'm making 8 CH bonds. If you are excelling at this, you could essentially realise that it's just 2 carbon-carbon single bonds being broken, 690, and 1 carbon-carbon double bond being made, 690, take away 611 does give you 79. However, the simplest way to make sure you definitely get all the marks is to add them all up. Either way, you've got the same answer because it's the same process. And that kind of leads in to the final part of this question. The actual value is plus 81. It's not that 79 that we just calculated. Suggest a reason why the actual value is different from the calculated value. So what you have to remember from the course is that all of these numbers are the average bond enthalpies, and make sure you write that in. However, that's where most people stop and they wouldn't get the mark. If you look up here, we broke 8 CH bonds and we formed 8 CH bonds, but the CH bond in ethene will be slightly different to the CH bond in propane, and both of these will be slightly different to the CH bonds in methane. So what you have to put, the calculation used average bond enthalpies, and then the crucial bit, which may not be the same as the actual bond enthalpies for these chemicals. And as you can see, it was a difference of plus 2 kilojoules per mole. It wasn't huge, but it certainly shows that somewhere some of these CH bonds were different from 415. Thank you.